Hi there, and welcome to our lecture on the structure of atoms. Looking at Atoms 2 of Unit 3. Our key ideas: what is the difference between protons, neutrons, and electrons? What do atoms of an element have in common with other atoms of the same element? Why do isotopes of the same element have different atomic masses? What unit is used to express atomic mass? So let's start looking at our first question: difference between protons, neutrons, and electrons. So those three items are the three main subatomic particles, and we distinguish or differentiate those by mass, charge, and where they're located within the atom. So looking at the proton, its charge is a positive 1. Its mass is 1.67 times 10 to the negative 27 kilograms. And it's located in the nucleus. Often what we do is just say that a proton is equal to 1 atomic mass unit. See if I get my pen work here. And we abbreviate atomic mass unit as AMU. We'll actually define atomic mass unit a little bit later in this lecture. The next particle we have is the neutron. It has no charge. It weighs relatively the same as a proton, so we're going to say that it's also 1 atomic mass unit. It's also located within the nucleus. And then we have an electron. It has a negative 1 charge. And we're going to say that it has a mass of 9.11 times 10 to the negative 31st kilograms. And this is approximately 1 out of 1,800, 1 over 1,800 AMU. So considerably smaller mass. And typically when we calculate the mass number, we ignore the mass of an electron entirely. So we just count the proton and neutron's mass to determine the mass of an atom. And then the electrons are located outside of the nucleus. So here's kind of a visual to see what we're talking about. A is represented by the nucleus here. So we've got the nucleus. Oops. Should be an E there. So this nucleus, you can say these darker ones are protons. These darker spheres are the neutrons. And then we represent the electrons out here on these rings. This is not actually how the atom is currently thought of, and we saw this in our last lecture, the atomic model in ease using the Bohr model, just because it's easier to count electrons and keep track of them when we want to use a model. So we tend to use this model still just because it's easy to use. Alright, so a little bit more about the atom. Each element has a unique number of protons. So if we change the number of protons, we're changing what the atom is. Unreacted atoms have no overall charge, so we consider those neutral. And this is because the number of protons and electrons are the same. So we have an equal number of protons, equal number of electrons, and this cancels the charges out. So we have an equal positive charge, an equal negative charge, and those end up being neutral. We have something called the electronic force that holds atoms together. So positive protons are attracted to the negative electrons by this electric force. So overall, this is going to hold the atoms together. Our next thing we're going to look at is atomic number and mass number. So what do atoms of an element have in common with other atoms of the same element? So atoms of each element have the same number of protons, but they can have different number of neutrons. And we'll talk about how they can have a different number of electrons later. But in order for an element to be what it is, we have to have just the right number of protons. So if we change the protons, we change the element. However, neutrons can change. Now, when neutrons change, the mass does change as well. So again, the atomic number equals the number of protons. And you can see down at the bottom here just kind of a sample. There's several different ways that the periodic table is arranged, and I think it just depends on the publisher of the periodic table, how they want to arrange the items on the periodic table. But they typically give you a key like this down here to show where the atomic number is, where the element symbol, what the atomic weight is, and then the element name. So this atomic number up here, and for carbon it's 6, is also how many protons carbon has. And then the mass number, we have an atomic weight down here, but the mass number is the total number of subatomic particles in the nucleus. So with the mass number, we typically count the protons, count the neutrons, add those together to give us mass number. So mass number, I don't think I have it on here. I do. Sum of the protons and neutrons. So we also have something called an isotope. The question is, why do isotopes of the same element have different atomic masses? So isotopes of an element will vary in mass because their number of neutrons differ. So I said before, we can change the number of neutrons, and because we have a mass on a neutron, about 1 atomic mass unit, it is going to vary the mass. So here's 3 isotopes of hydrogen. We've got what we call hydrogen 1, hydrogen 2, hydrogen 3. These have specific names: protium, deuterium, tritium, and this just tells us how many particles are within the nucleus. So protium, or hydrogen 1, has a single proton in the nucleus and 1 electron outside. On hydrogen 2, we are adding a neutron. We still have 1 proton, we have 1 neutron and 1 electron. So the overall charge is still neutral because we have the same number of protons to electrons, but we have a neutron now, so our mass increases by 1. And tritium here, or hydrogen 3, has an additional neutron, so we're adding yet another mass, another atomic mass unit to that atom, and we have the same number of electrons to the protons, so it's still neutral. Some isotopes are more common than others. We have something called a radioisotope. These are unstable isotopes that emit radiation and decay into other isotopes. Number of neutrons can be calculated. So if we want to know how many neutrons an atom has, we can take the mass number. If we have the atomic mass, which is typically a number with some decimals, we can round it to the nearest whole number to get our mass number, and then we subtract off the atomic number to give us the number of neutrons. So for example, we've got chlorine here that has a mass number of 35, atomic number of 17. So I can subtract those two to give me 18 neutrons. An isotope of chlorine is chlorine 37. Same number of protons, or same atomic number. So 37 minus 17 gives me 20 neutrons. So a little bit more on atomic masses. What unit is used to express atomic mass? Because working with such tiny masses is difficult, they are usually expressed in what we call unified atomic mass units, or just simply atomic mass unit. So we define atomic mass unit as a unit of mass that describes the mass of an atom or molecule. It does go on to further define atomic mass unit as exactly 1/12 the mass of carbon atom with the mass of 12 atomic mass units. Don't worry about this last part. It's more for chemists to know what it is. Basically, atomic mass unit is just the unit that we use to measure the mass of an atom or the mass of a subatomic particle. Average atomic mass is a weighted average because we have a different number of isotopes that we find that naturally occur in nature. We have an example. Chlorine-35 is more abundant than chlorine-37. So chlorine's average atomic mass ends up being 35.45, and we're going to change this to AMU. So instead of having a U here, AMU. I should say that some resources, some textbooks use just U instead of AMU, so you can see U as well. But 35.45 is what the mass ends up being, atomic mass of chlorine, because we have isotopes of 35, or chlorine-35, so we have a different number of neutrons. We also find chlorine-37. But because we find more of the chlorine-35 occurring in nature, this number does end up being closer to 35. So that's why we can round this mass, atomic mass, to 35, so nearest whole number, to give us the mass number. So here's a visual pie chart. Chlorine-35 occurs naturally 76% of the time, and we've got chlorine-37 that only occurs 24% of the time. So the overall average that we find in nature ends up being 35.453. So, thanks for listening.